All right, so today I'm going to talk to you about Gröbner fans. And really what I mean is I want to introduce a Gröbner fan, and so I'm going to talk to you a lot about monomial orders. We'll use those to define initial ideals, and that'll show us what a Gröbner basis is. And then we'll put all of these concepts together to see what a Gröbner fan actually is, and then look at some pretty pictures of specific Gröbner fans. So, let's start with the monomial order. So a monomial order on a polynomial ring and here I just want K to be a field. I don't care which one. This is a total order on the set of monomials. Alright, so my set of monomials just looks like this, where I'm going to use this notation x to some Greek letter to really mean x1 to the a1, x2 to the a2, and so on. Right? This notation will make things a little simpler in some cases. So it's a total order on this set of monomials, such that. So the first thing that I need is I want this monomial order to play well with multiplication. So if I have, let's say, some monomial order denoted with the less than sign. So if I have x to the alpha less than x to the beta, then I don't want this order to change if I multiply by x to the gamma. Right? So that somehow this order preserves, or the order is preserved by multiplication of other monomials. And the other thing I want is that x to the 0, which is 1, I want that to be my smallest monomial. All right, and that's it. That's what a monomial order is. And the standard examples I'll sort of describe them briefly here. So we have the lexicographic order, and the word lexicographic has something to do with dictionaries, and so this order basically behaves like a dictionary in the sense that it sorts the monomials like a dictionary sorts words, which means it looks at the first letter, and then if there's a tie, it looks at the second letter, and so on. Right? So let's say our lexicographic order is where so list this in steps. So first, look at the x exponent. Bigger one wins. Then look at the y, or x2 exponent. Right? And so on. Right? And when you get down to your last one, your xn exponent, you'll have resolved any possible ties. Right? So there can't be any ties after that. So that's lexicographic. Then we could also, maybe we have a graded ring and we want to keep track of the degree, right? So maybe let's look at an example of lexicographic first. So the example here is if I have x squared z squared and say like x y to the 4th times z, the first rule in lexicographic, the first step is to compare the x exponents, right? Here I have a 2, here I have a 1, that's all I need to do. And so this is bigger by the lex order. Right? I don't even care about the y's and z's here because I didn't have a tie. Okay, so the next monomial order, like I said, is maybe you care about having your degree play a role in this order somehow. Sort of the total degree, you want it to play a bigger role. So The way that we can do that is with graded lexicographic order. And the way this one works is really similar, but at the beginning, we're going to first compare the total degree. Right, and then break ties with lex. Right, so this is the first step, and then if we tie on the total degree, then we go to this list and start looking through there. So an example here is if I have, say, well, let's just do the same ones that we had before. With z. So here, the first step is to look at the total order, or the total degree. And here we have 4, here we have 6. So we don't even need to look at the individual exponents, right? This one on the right is going to be bigger. And I'll write that with a little glex next to my order. Okay. There's one more kind of standard monomial order, and by standard I just mean like when it shows up on Wikipedia. So this is graded reverse lexicographic.
These also show up in ideals, varieties, and algorithms that look.
Yeah, definitely. Yeah, so any time that you like are introduced to monomial orders, you're likely to see these three. They might show you other ones as well. So then GrevLex is, or sorry, graded reverse lexicographic order is, okay, we do the same first step. So start by comparing the total degree. But then instead of doing lex to break ties, we're going to say that we want to favor having fewer, let's see, how do I, fewer later variables. Right, so the example here is not written down, but let's do like x squared, y squared, z squared, and x, y to the fourth, z. Right, so these both have total degree 6, so we have to go into the second step. Now we want to favor fewer later variables. So what do I mean by that? I mean that since the last variable that I have is a z, I'll start by comparing those exponents, but instead of giving this one the win, since it has 2 and this one has 1, I do it the other way around. I give it to the little guy. Right, so this is, and the shorthand here for this long name is GrevLex. And I'll start using those notations from now on. Okay, any questions so far?
Is the last one the same as the first one if you reorder variables, or is it not the same?
In some cases they can be the same, but in general, no. You're saying that is this one the same as this one up to reordering x, y, and z?
Yeah. No.
Not in general, no.
For 2 variables.
Okay.
Is there any example you can give of one that's not comparable in graded lex that is in graded reverse lex, or?
I can take this example.
Not on the fly.
Or is this example one of them maybe?
Yeah.
Because, wait, x squared, y squared, z squared. So if you compare the total degree and then lex, so it's still less than in graded lex order, right?
No, definitely he's greater than.
Yeah.
X
squared is bigger than
than
x. I see. Okay.
Oh,
correct.
you do the first degree, it's bigger. Oh, I see. Yeah, got it.
Cool. Questions are resolving themselves.
Interesting.
But Mark was asking, well, maybe it's because you have to reorder the variables, but that won't fix it. They're different. You can't reorder again.
Right. I mean, so there are going to be situations where, like Chris was saying, like in 2 variables where some of these things are going to be the same. But those are going to be, that's not generally what happens. Right? So in general, these are all giving a different way to order these monomials.
I also just realized that none of these are what I would think of as lex order, which is like over there, even though over there in lex order, I would think like xxz, z, the x squared z squared. xxz is like an earlier word than xyyyz, right? Because like if you're doing alphabetical order on like words, more x's would be less. So you could also use that order, I think, but it's not one of the ones that is usually used for Gröbner cases.
So it's just kind of like a different Lex order. in some
Yeah,
sense,
like
right?
Lex order by looking at the words where you expand them out and you think of an x squared as just xx and like do alphabetical order on those words, right?
Right. So maybe just to resolve any still ambiguities about how these things work, let's just sort these four monomials using each of these three monomial orders. So do Lex, G-Lex, and Gröblex. And we'll just rank these. So Lex is usually the easiest one, at least for me to do by hand. And so I can just look at the XX one here is 2, 2, 1, 1. So if one of these two is going to be the winner, and I need to break ties by just going down the list. So here I have 2 Ys, here I have no Ys, so that one wins. Of course, this one will come in second. And here I need to break the tie as well, but here I have 4 Ys, and that only has 1. So I get 3 and 4.
So here, a smaller number means it's larger?
No. No, I start with my exponents on x, and then I want them to be big if I want to win.
But you're saying the bottom one here is the smallest?
Yes.
It is the smallest by Lex ordering, but it's because it doesn't seem...
Sorry, I mean like
see
you gave it a 4 here. It's like larger number.
Oh yeah, larger number here, yes.
It's
Yes,
like
this is
running
the
a race,
ranking.
first place wins.
First place is biggest.
I see.
Yeah.
Monomials are really competitive. Okay, so the G-Lex setting, we start by looking at the total degree, right? So total degree here is 6, 4, 6, and 14.
Oh.
So without looking at anything else, I know that that one's going to be the winner. Then second place goes to one of these two, and I have to break the tie by looking at the Lex order, right? And so this one does better in Lex, so it gets second, and then of course this one will get third. And then Gröblex is similar by saying like the total degree is still going to win here, but then in this second and third place tie, it's going to work out differently, right? So now these are both the same by the first step of Gröblex, which is just comparing the total degree. But then I compare by saying I want fewer later variables. So now this one has 1z, this one has 2. The 1z ends up winning. So this one's 2, now that one's 3, and now it's 4. One thing I want to mention here is that I have not really defined what these orders are in a lot of words, right? I've kind of just told you how to compare monomials using them. And just want to emphasize that each of these steps can actually be encoded with a dot product, right? So I'll say each, let's call it a comparison step. So I can understand these in terms of dot products, and this makes it feel a little bit more math-like, right? But the dot product that we're looking at here is between exponent vectors. Right, so the exponent vector of x, y to the fourth z, for instance, would just be 1, 4, 1. So exponent vectors, and then what I'll call a weight vector. And so let me just show you a quick example of this. So let's say for graded Lex, this first step, I say I'm claiming that I can encode that as a dot product of monomial exponent vectors with some weight vector. And the weight vector that I want to use here is just 1, 1, 1. So let's see how that goes. So I'll use the same example here. So x squared z squared has exponent vector 2, 0, 2. And I don't have any y's. And so then I take this dot product, and I get 2 plus 0 plus 2 is 4. And I can do the same thing with x, y to the fourth z, right? This thing's exponent vector is 1, 4, 1. I'm dotting it with the same weight vector, and I'll get 1 plus 4 plus 1, and that's 6. And so somehow, the 6 being bigger than the 4 is the reason that this favored this one. right? And of course, if we had a tie, then we'd have to go to the next step, Lex, and then we'd have to go through this process again with a different weight vector. And that next weight vector would end up being 1, 0, 0, because we care about the x exponent. Okay? So we'll come back to this idea of weight vectors towards the end. It'll be important for seeing what the actual Gröbner family is. Okay. Right. So. One other thing I'll say about weight vectors here is that they can't be negative. Right? So if I tried to do, let's take the example we just had, and now I tried to dot with, say, 1, 0, say 1, 1, minus 1, right? The problem with putting in a negative here is now, well, for a general monomial, if I have just z to some power, well, let me just say it like this. If I take something here and dot it with 1, 1, minus 1, it's going to order the z things badly, meaning that somehow like z to the third is going to be less than z squared, it's going to be less than z, which is going to be less than 1, and we can't have it. So in these weight vectors, we require that all of the entries are positive.
Not negative.
Not negative, thanks. Okay. So now we can sort of move on and use these monomial orders to build some more interesting things. So the initial term of some polynomial with n variables is the largest monomial in F. Again, to even say the largest monomial, we need a monomial order, so with respect to some fixed monomial order. Right, so it's the largest monomial in F, along with its coefficient. And so, kind of what you want it to be. And then, I'll just give you another definition right away. The initial, so let's say for a fixed ideal, I, and again we'll fix a monomial basis, or a monomial order. The initial ideal of I is denoted like this. We put the monomial order in the subscript, and we just say is the ideal that's generated by the initial terms of F, such that F is in I. And this is I didn't write this, but that's the notation for the initial term of F. And we want this to be for like really all of the elements in our ideal, right? And so at first glance, we might hope that if I hand you, some generators for an ideal, and you just look at the initial terms of those things, that those are going to be enough to generate your initial ideal. Unfortunately, or fortunately, depending on how you look at it, that's not the case, right? So let's see an example of how things can go wrong. So let's fix the monomial order to be Lex, and use this ideal here. So still 3 variables, x plus y plus z, xt cubed plus z plus y squared. Okay, so what I'm going to do first is just find a new element in I. Right? So I can take this xz cubed plus z plus y squared, and then I'll subtract off this, but I'll multiply it by z cubed. Right? Really, I'm trying to make this thing sort of go away somehow. And so I get z plus y squared. That goes away. You know, xz cubed minus xz cubed. I get minus yz cubed minus z to the fourth. Right? And what's the initial term here? Well, again, we're using Lex, so we just look for the biggest y, and it's that one. Right? And okay, so I'm saying that y squared is in I, so something in I, so its initial term needs to be one of the generators for the initial ideal. So y squared needs to be in here. But if we tried to just generate the initial ideal right off the bat without doing this, you know, the initial terms that we started with were x and xz cubed. And y squared is not in the ideal generated by x and xz cubed. Right, which is, I guess, just the ideal generated by x. But so that's the big idea, is that you know, general basis for an ideal is not in general going to have the property that I can just look at its initial terms of the generators and get the initial ideal. So instead of showing you how we can go through and sort of make that happen, I'll just define Gröbner bases to be the thing that fixes this. And so the Gröbner basis for I, and again, with respect to some monomial order, is, well, it's a basis for I. So some list of polynomials, G1 through GR, such that the initial ideal of I really is just generated by the initial terms of the generators. And so it's just defined to be the thing that works. And so kind of to relate this back to the example, if I just throw in, so if I just take the two polynomials that I started with, and then I throw in this new polynomial that we computed, and this is a Gröbner basis, right? And I'll denote the initial terms like this, right? But it's, yeah, so I guess I'm claiming that without too much support of it, but I'll write down a fact that'll justify that. And Chris gave me this fact yesterday, so if it's not true, he can correct it in real time, or you can go to him and complain. So the fact is that if I have some list of monomials that generate the initial ideal, and another, list of polynomials that are in I, such that the initial terms of each of the FIs is exactly the MI, then this set is a Gröbner basis. I get that right? Mm-hmm. Cool. So, yeah, if we have polynomials such that the initial terms match up with the monomials we need to generate the initial ideal, then we know right away that it's a Gröbner basis. And since I can have this thing and that thing, then I've generated my entire initial ideal, right? Which, I don't say what that is. Okay, so I forgot to mention that the initial ideal here is generated by just x and y squared. And again, I'm just claiming this. But since I have, these are my M1 and M2, and then I throw in F1 and I guess F3, and now I've got a Gröbner basis, and this thing being redundant doesn't stop it from being a Gröbner basis, right? Which leads to the next sort of problem, which is that Gröbner bases aren't unique, right? Even for a specific monomial order, I can have multiple Gröbner bases, and there's a way we get around these, or around this. We just do what we usually do, find an adjective that works. So reduced Gröbner bases are unique. And so I'll just show you that in this example, we can just throw out the redundant term, if you will, the xc cubed term. And I get y squared minus yc cubed minus c to the fourth. So this I claim is a reduced Gröbner basis, and I won't write down the definition for reduced. I'll just show you what it means. It just means that this, the initial term of this thing doesn't divide any of the monomials in that thing, and vice versa. So x doesn't divide any of these, y squared doesn't divide any of these.
Two questions. First one, do Gröbner bases always exist?
Yes.
Okay. Second one, is there some sort of like bound on the number of generators you would have in a reduced basis based on the number of generators you have for your original ideal?
That's a really good question that I don't know the answer to. I want to say
The answer
yes.
is, there is a bound, but it's horrible.
Is it really bad?
Yeah, it's doubly exponential.
Oh.
There's the Mayer-Meyer examples, which are like terrible. But there is a bound.
Well, I was curious if it was just the same number, because this one we had 2 generators and then 2 generators, but I guess not. And that's an example that proves that that bound is tight.
I don't know. I don't.
Can I ask a question too before you raise?
Yeah, please. Oh.
Well, it's probably okay. Sorry, so how do you, if you just have generators for an ideal, how do you compute the initial ideal?
That's a good question. So the answer to it is kind of the same as the answer to Kyle's question of like, do Gröbner bases always exist? So we can compute Gröbner bases using an algorithm, Bootberger algorithm, or I guess there's better algorithms now. But that's going to give us, there's a correspondence between all of the, different kinds of Gröbner bases we can use and the different initial ideals that are going to come out. And so the way that I would answer that is you would compute a Gröbner basis, and then that's going to tell you what the initial ideal is.
Okay, so I'll just wait and see, I guess.
Well, but you're not going to cover that.
I'm not going to go into,
There's an algorithm that, from a list of polynomials, it'll keep sort of doing kind of what he did. You'll keep exposing new potential terms.
Yeah.
And then there's another algorithm that tests that what your list is there's no more terms.
You can kind of see eventually that
Yeah, there's.
once you start
Yeah.
generating. Okay.
Yeah, so it would take a fair bit of time to go through kind of the algorithm of how to compute these Gröbner bases, but just like Chris said, it kind of is like how we got this thing from the last thing. You're looking for new elements of your ideal that have different initial terms, right? So you're trying to discover those initial terms, and there is an algorithm to do this, and the Gröbner basis always exists, but that's not the focus of this talk. So I'm going to now do a really simple example.
Can I ask?
Yeah.
So the Mayer-Meyer one, which order for that?
I don't remember. I just remember that there was an example that was sort of.
Or
That's horrible.
I see. I was just.
And it was sometimes used to show that, like there's this is a metaphor, but like the simplex algorithm is, you can prove that it's terrible, right? Because it's this worst case thing, but everyone uses it because it's great. Gröbner bases are the same. You can prove that it's terrible, but not everyone, but a lot of people use it because it's great. But it doesn't, So there's, to construct an example, it's an example that somehow you don't run into examples like that when you're doing algebraic geometry, but you could.
Yeah. I was curious because G-Rex is very faster than just Lex or something. So
Yeah, so it's probably a Lex of some sort.
I see.
Cool. So let's look at a really simple example where we just have a single, and our ideal is just generated by a single polynomial, right? So really quickly we can write down what the Gröbner bases that we can have are. So I can have x plus y squared, where x is the initial term. Or I could have the other way around, right? And this one, I guess, would be like graded lex. And these correspond to initial ideals, right? So, right, like in lex is the ideal just generated by x, and here this initial ideal will be generated by y squared. And remember earlier on I was talking about how we can interpret the comparisons here as weight vectors. Right, and so let's look at that again. So if I have x, the exponent vector here is just 1, 0, and for y squared, which is 0, 2. And so we can kind of look at a general weight vector, say a comma b, and just look at what's going to happen here. Right, this is like doing sort of a general comparison set of these two monomials, and okay, here I just get A, here I get 2B. And if, this AB step, so if A is bigger than 2B, then this thing's going to tell me that x should be bigger than y squared. If it's the other way around, it's going to tell me that y squared should be bigger than x. But what happens if A is equal to 2B? Well, then we get a tie, right? And the way that we were looking at these monomial orders before would say we need to go choose another weight vector. But I want to look at a slightly different approach to solving this problem. So instead, let's just look at the space of possible weight vectors. So here's A, here's B. So let's look at an example. Let's say if I have the weight vector 3, 1, and that's a situation where A is bigger than 2B. So x should win, right? So here is 3, 1, and this corresponds to x winning, so this is like lex. And if I do the other way around, let's say just 1, 3, then this is going to correspond to g lex. Then we have this space of ties, which is where A is equal to 2B, and okay, so that's like here, but really I could have had, so what's an example of this? It's like 2, 1, where we'd have a tie. But really anything with this ratio is going to give me that tie. If I have 4, 2, or 6, 3, or whatever. And so, just drawing this whole line, everything on here is bad. Right? It's going to give me a tie. It's not going to resolve this question of is x bigger than y squared, or y squared bigger than x. It's not going to resolve it with one of these vectors. But anything up here will resolve it in the g-lex case. And anything over here will resolve it as a lex case.
Why 1, 3 is G-Lex? Like, what does that mean?
Because if we dot with 1, 3 here,
Yeah.
we'll get 1 for A,
Yeah.
and we'll get 6, right, for y squared.
It usually it acts like G-Lex on this particular example.
Yes.
In fact, when there's this one polynomial, and if you just got to figure out how to order things, and so it's not actually G-Lex, but it's sort of you can't tell the difference between it and G-Lex on this example.
Right. So in general, a single rule, a single weight vector is not going to be enough to sort all my monomials. But when I'm looking at a finite set, like here, I would just have 2, then I can get a total, most weight vectors are going to totally resolve this question of which one's bigger, right? So all of these ones work to resolve it. They'll make it go one way. All of these ones will resolve it a different way. And everything along here does not work, right? This is the space where I have a tie, so I don't have an initial ideal. I don't get a Gröbner basis there.
So over that line, we can give a monomial order, but why we are not having Gröbner basis?
So I'm just saying that any point you choose along here that looks like, you know, let's say 6, 3. Any one of these, when I try and take the dot product here with A and 2B, they're going to be equal. And so I'll end up with a tie. And since it's tied, I don't know if x or y squared is bigger. Now, I can actually go and get my hands on a monomial order, like really pick Lex or G-Lex, and then figure out which one's bigger. But I'm trying to somehow substitute weight vectors for these descriptions of monomial orders.
So some level you say, look at all the Gröbner bases he could possibly get on this example. And there's only 2. For each of those Gröbner bases, he's able to define a cone. For each of those possible Gröbner bases, like, you look at all the things that put the x first. There are only 2 Gröbner bases you can get on this particular example, this ideal with one generator. You either have this term first, or you have this term first.
Yeah.
And so he's just saying which ones agree with that.
Yeah, so one way of looking at this picture is just in here, right, this positive ortho here is just all of the different monomial weight vectors that I could do, corresponding to all of the rules, right, the comparison steps that I could possibly do. And some of them resolve this in a single step and give me a Gröbner basis, and then a few of them don't. Right? But this picture contains, it tells me how many Gröbner bases I could possibly have. Right? So how many monomial, like distinct monomial orders are there? In this case, just 2. But we'll see that gets bigger. So this is the first example of a Gröbner fan, is this object here. And I'm not actually going to define the Gröbner fan because there's a bunch of words, like Chris was saying, cones and things like this, but the pictures hopefully will be more or less self-explanatory. So yeah, the Gröbner fan here is sort of this entire region, I think, fan, if you know that term, going off forever and just looking at all of those different weight vectors.
So Gröbner fan of I, in this case?
Gröbner fan of I. Yeah, and notice that the Gröbner fan doesn't depend on a monomial order like most of the objects that I've introduced, because it's sort of showing you how the Gröbner basis changes with respect to that monomial order. And so it's showing you all of the different things that can show up. Okay, so here we don't really need to look at everything. I could just look at, I could sort of capture all of this information by just looking at a slice of this thing. Right? So maybe like where x plus y is equal to 1. And it'd be kind of a weird picture, right? But I'd have like a segment here, and then I'd know that there was a transition here into a different Gröbner basis here, right? And the reason I'm doing that is because I'm really bad at drawing things in 3D. And so I'm going to use this idea to kind of illustrate the next example. So before I get into the example, I just want to, so if this is my, right, so the next example is going to be in 3 variables. And so my weight vectors are going to have 3 variables. And the pictures that I'm going to draw aren't going to be like these, like a 3-dimensional fan kind of thing. I'm going to do what I did here. I'm going to look at a slice. Like this. Right? And if you like, this is x plus y plus z equals 1.
Or a plus b plus c.
Oh, sorry, yeah. Thank you. Yeah, so the pictures that I'll look at are literally just the slice so that I can kind of have a nicer 2D way of writing these things down. Okay, so the example the ideal will be one we've seen. Z cubed, C to the 4th don't have initial terms yet because I haven't said what my monomial order is. But if I say I use weight vector 5, 4, 1, and I can look at what monomial order I should get. So the initial, I think we saw earlier that the initial ideal with respect to Lex of this ideal was just x comma y squared. Right? And really we're just asking, do things get shuffled around by this vector in a way that's going to mess this up? Right? And so if I'm giving 5 weight to all the x's, then this is going to be bigger than that, is bigger than that, because 4 and 1 are both smaller than 5. So in this, in Lex, this is the biggest term, and again in Lex, this y squared is the biggest term. And so we can say that this initial ideal agrees, right? This weight vector agrees with Lex here. And so I'm going to just throw in this notation where I put the weight vector in the subscript of the initial ideal. I notice, again, from before, if I was to be dumb and choose this weight vector right here, that wouldn't give me an initial ideal. So I couldn't write in sub 2, 1 here of I, that wouldn't be meaningful. Right? It just wouldn't give me an initial ideal. Okay, so 5, 4, 1 gives me Lex, and let's see. But if I was to try 4, 3, 1, then things go wrong, right? And so this is still fine, right? X is still bigger than y, bigger than z. But now y squared has 6, right? It gets weight 6 with this dot product, and yz cubed also is going to get 6. Right? So this weight vector does not, we get a tie between y squared and yz cubed. Right? This weight vector doesn't know which one's bigger. And so the picture that I want to draw is, again, it's this picture here, the red triangle, but a little more interesting. There's stuff going on the inside. Okay, so make sure we understand the picture first, so I can at least label these vertices 0, 0, 1, 0, 1, 0, and 1, 0, 0. And I'm going to just kind of consider, so like the vector 5, 4, 1, it passes through this slice somewhere, and I'll just kind of denote it that way. I guess if this is the slice a plus b plus c equals 1, then I would draw 5, 4, 1 in this picture at 5/10, comma 4/10, comma 1/10, right? And, okay, so let me just draw this quick. Okay, so 5, 4, 1 ends up being right here. Right? Again, you can really think of this as 5/10, 4/10, 1/10, but it's equivalent. And that means that this cone here corresponds to Lex, right? Because we saw that 5, 4, 1 agreed with Lex in its initial ideal. And so all of the weight vectors in here will give me Lex order. Right? But we saw that 4, 3, 1 gave us a tie between y squared and yz cubed. And that's because, this is exact, but 4, 3, 1 sits on this boundary here, right? And so this is sort of trying to, it's trying to satisfy two different Gröbner bases at once, and it just fails to define one at all. And yeah, so we can if we really look at this, we could say that a weight vector that looks like 3 plus epsilon 3 comma 1, this is always going to give us this tie problem that we have. And that's just going to give us all of the things along this line. Right? This point here is 3, 3, 1. And if we just add epsilon to that first thing, you know, we kind of get, you think about 1, 0, 0 as sort of the point at infinity, right? But all of these are described by weight vectors like this.
So just as sort of an overview, there's 6 regions in here. If you look at all possible monomial orders that exist and look at the reduced Gröbner basis of this particular ideal, the claim is that there's only 6 things that would appear. That's a strong statement, but there's a theorem that takes this proof out. There's only a finite number of reduced Gröbner bases that can show up among all possible monomial orders for this ideal. It turns out there's 6 of them. For each of those Gröbner bases, there's a particular term that you can underline, which is the biggest term. And then, well, what distinguishes that is that that bigger term is, that leading term is bigger than all the terms after it, and the other ones, that term is bigger than all the ones after it. And that you can cut down with a system of inequalities, which cut out convex polytope. And these are the convex polytopes.
So each wall is where like 2 different monomials get
Yes.
switched.
Exactly.
Cool.
Don't be done talking amongst yourselves yet. This was working beforehand. Does anyone know how to get the HDMI?
Oh, there it is.
Oh, here we go.
Good job,
Cool.
Chris.
So I'll leave that up for a second while I talk about what it is. Obviously, it's a Gröbner fan. It's the same picture we're looking at here, but of a different ideal and flipped upside down. But so you'll notice that this thing here. I'm not drawing that for you. There's one extra thing in here. So this Gröbner fan here, you know, it's got, feels like there's some symmetry. It's almost attempting to be symmetric, but it's not really that symmetric. And this thing over here is obviously, you know, has nice symmetry, kind of the way you might expect. And what's going on here is that, you know, if I just take any specific ideal, it's likely to favor some variables over other variables, right? And if I take that ideal and look at all of its generators and sort of do a random change of variables in some sense, then it should stop favoring x over y over z, or vice versa, right? Like there's no real winner in terms of one variable being better than any other. Everyone's kind of just the same because we shuffled them all around. And since this is a geometry seminar, geometrically, we can kind of think about this as like a specific ideal is remembering how a variety sits in space. And when we shuffle the variables around, it's remembering some things about the variety, but just not how it sits in space, right? And so that's what's going on in this picture, is I've shuffled the variables around to make this thing end up being symmetric, right? And so these things are called generic initial ideals, and they're actually well defined. But I'll just end with some cool pictures here. So this is the Gröbner fan that you get if you take a general affine, not homogeneous, cubic, quadric, and a linear. In 3 variables. If I just do a cubic and a quadratic, I get this thing. If I do 3 quadrics, I get this. If I do a cubic and 2 quadrics, I get that one. And the last one's 2 cubics and a quadric. And they're really pretty. This one has like a few little issues, like it's not quite symmetric in the drawing, but probably just a rendering issue.
What does that symmetric fan, GB fan, supposed to mean? I didn't get.
So this is the Gröbner fan of a specific kind of ideal.
Like in geometry.
Oh, well, that's an open question.
So
Well, the symmetry is, if you take an ideal, it knows both its, all this Gröbner fan knows both geometry information and how that variety is sitting in space. Like you think of, like if I have a line and I project down, I get a point, but if I do a random, if I sort of do a random change of variables, the line's gonna be like this and its shadow is always gonna be a line.
yeah.
So you get rid of the information about how it's sitting in space and you focus all the information on geometry. At least that's the metaphor. It's a philosophy statement. And so this is, each region in this, you look at all possible reduced Gröbner bases that you can get for all possible monomial orders. The fact that there is an algorithm to do that is amazing. Okay, so that's, so this is from, you use a program that, someone had to do a lot of work to prove that and then implement it. Okay. So, but given an ideal, you can make it, you can generalize it by doing a random change of variables. So it's the same variety in some sense, right? It's just sitting in space differently.
Mm-hmm.
So yeah, just to wrap up here, again, just to reiterate, each of these, cells in here, which really are called cones, corresponds to a different marked reduced, reduced Gröbner basis. And the fact that there's the symmetry here just corresponds to the symmetry of ordering x, y, z, or x, z, y, etc. Yeah, thank you. Yeah.
There might be a part of questions, at least with one of them. So first of all, with this one, you said that that region marked by 541 is Lex ordering. Do you know what any of the other ones are? Like, is one of them GrabLex or something like? Do you know what the other ones are?
I don't, but you could figure it out.
Okay.
Definitely one of these cones corresponds to GLex and GrabLex. And yeah, you can figure that out.
Okay. And then, so with these fans, if you were given some arbitrary collection of like regions where they're all convex, is there an ideal with that Gröbner fan?
Say no.
I'd say probably not.
I would doubt it. Because with low degree polynomials, you're kind of going to be limited on how much you can get, and there's a lot more pictures you could draw than things I could ultimately get.
I see.
So this like having a basis of generators and then trying to find a Gröbner basis, it reminds me a little bit of in our algebraic geometry class. If you start with like a ideal for a variety in affine space, and then you want to find generators for the ideal of the projectivization, you cannot just homogenize generators of your original ideal. You may have to use different generators. Is that related to this in any way?
Yes. So if you have a Gröbner base, I think you can homogenize a Gröbner basis.
Yeah.
But the other thing is, like, in general, if you have a set of generators, you can homogenize your generators, but then you have to quotient out with the thing at infinity, sort of do an ideal quotient.
Yes.
And that's also a Gröbner basis algorithm.
I see. So that's exactly answering. This exactly answers that.